Okay guys, so today we're going to continue on our path towards understanding motion. And yesterday we talked about constant acceleration type problems, and we looked at deriving the kinematic equation. Okay? When we derived those kinematic equations, we came up with these four equations right here, which we are going to be using extensively. I just put them up here as a reference so we can talk about them today as we go through this problem. If we look at this problem, guys, it says a drag racer accelerates from rest at 21 meters per second squared for 3.2 seconds, okay? Then travels at a constant velocity for 4.4 seconds. You can kind of imagine the drag racer getting up to top maximum speed and just going the rest of the race at top speed. And then at the end of the race, a parachute deploys and stops the car in 8 seconds. So how far did the car travel over the entire trip? Okay? Now, in order to get this, we're going to have multiple levels, multiple steps. Okay? If we look, guys, what I've kind of done up here is I've broken, I think pictures always help, and I've broken down this drag racer's trip into 3 sections. Okay? If we look at the sections, here at the beginning, his velocity at the beginning of section 1 was 0. He traveled for 3.2 seconds, and at the end of that, he's going to have a certain velocity. Okay? Now, we don't know what x is, and we don't know what that velocity is, so we're going to come and try to find those when we work through our kinematic equations here. Okay? Then, he travels a constant velocity across this section, which I think you guys would agree, whatever his final velocity is for section 1, is that going to be his initial velocity for section 2? And is he going to travel that same velocity all the way through that section? Which would say that our velocity 2 is equal to velocity 1, and then our initial velocity for the third section is going to be equal to the final velocity of section 2, which is also equal to the final velocity of section 1 because he's going a constant velocity. Does that make sense? Okay. And then in section 3, section 2 is going to last for 4.4 seconds. And then section 3, he has an initial velocity. We know that he's coming to rest at the end, so his final velocity at the end of section 3 is 0, and we know the time for section 3 is 8 seconds. Does that picture kind of tie everything together? Yes.
When you use section 1 down at the bottom for acceleration, is it supposed to be 11 or 21?
Oh, you know what? I changed it in the middle of the problem, so thank you for pointing that out. Let's put 21 there. Okay? When I did the problem originally, he was going 11, didn't get him going faster. Okay? All right, so let's check this out. In section 1, we know its initial velocity, because he's coming from rest, is 0. His acceleration is 21, and his time that he's going to be going that is 3.2 seconds that he's going to be accelerating. Now, guys, you'll notice I put x because we are trying to find the total distance at the end of this problem. And we also need to know the final velocity because we need to know the final velocity here to get the initial velocity for the second section. Does that make sense to everybody? Okay. So let's go in. If we have these 4 variables, the kinematic equation that we're going to choose is the one that contains all those, which happens to be V equals V naught plus AT. And then I've annotated it with section 1 throughout. So my final velocity at the end of section 1 is going to be equal to my initial velocity, 0, plus my acceleration times the time I'm going to be accelerating. You see that? Okay. In our motion packets, remember when we were accelerating at 2 meters per second for 5 seconds? That meant that we were going to be going 10 meters per second at the end, just 2 times 5, which is what we're doing here basically. Okay. Now, that gives us our final velocity at the end of section 1, which is also the initial velocity of section 2. Are you kind of with me? Okay. Now, we also, in order to solve this problem at the end for how far the car travels, we also need to find the distance traveled during section 1. Okay, so armed with these 3 and looking for x, the equation that I chose was x equals v naught t plus 1/2 at squared. Now we know that our initial velocity is 0, which makes that term go to 0, which leaves us basically with only this term. So the distance traveled is going to be 1/2 21, which is our acceleration, times 3.2, which is the time squared. Okay? Which gives us 107.52 meters traveled. Now, just so you guys can see a different kinematic equation and a different look, okay? Did we solve for this right here? So we could use this guy, and this guy to solve for that, right? Instead of time. So you'll see what I've done is I chose v equals v naught, v squared equals v naught squared plus 2ax. And when we plug those numbers in, noticing there's no t component here, do we come up with the same distance? Right. So multiple ways using the kinematic equations to come up with the same answer. Okay. So you'll notice the distance traveled was 107.52. Now over here at the very end here, I'm going to add all my distances together. So I'm plugging in that distance for section 1 right there. Okay. Now if we come back here, and this one is kind of interesting because you'll notice in section 2, I don't use a kinematic equation. Why don't I use a kinematic equation? Because in section 2, he's going a constant speed. He's not accelerating, right? So if he's not accelerating, then we go back to the stuff that we worked on before. Velocity simply is equal to delta x over delta t, right? Okay. So if we want to find the distance, we can just multiply both sides by delta t. So our distance traveled is going to be our average velocity times our time. And guys, the ending velocity for section 1, is that going to be the beginning and the constant velocity through the whole section 2? Okay, so that's all I'm going to do here is take that velocity, 67.2 meters per second, times the time that he's going to be traveling at that velocity. And that should give me the distance traveled for section 2. Make sense? Okay. Now I've taken that distance and plugged it in over here for x2. And to find the total distance traveled, that's all we're going to need to now do is to find the distance traveled in section 3. So if we look at section 3, is the initial velocity for section 3 equal to the velocity at the end of this one and the velocity all the way through there, which turns out to be 67.2. Okay, so you'll notice I put 67.2. The parachute's going to bring the car to a stop, okay, and it's going to take 8 seconds to get that done. So we know those 3 variables, but we don't know x. Now if you look, that kinematic equation that contains those 4 variables is x equals 1/2 final velocity of section 3 plus initial velocity of section 3 times the time for section 3. Okay, so if we look at that, we got x3 equals 1/2 67.2 plus 0, because at the end he stopped, times 8 seconds. And we come up with a distance of 268.8 meters traveled during section 3 of the trip. Quite simply, we found distance traveled in the first section plus distance traveled in the second section plus distance traveled in the third section. We add those all up right here. We come up with a total distance traveled for the drag racer of 672 meters for the entire trip. Okay? Now, I designed this, and I don't think it's perfectly realistic because I think drag racers go a little bit faster than this. But if you add section 1 and section 2 together, you come up with about 400 meters, which is about a quarter of a mile, which is what usually drag racers race, about a quarter of a mile. Does that make sense? Okay. Now, the thing that I like about this problem, guys, we basically got a chance to check out that kinematic equation and its use, this kinematic equation and its use, that kinematic equation and its use, and if we come over here, this kinematic equation and its use, which basically summarizes, I think, all of the kinematic equations. Okay? The only thing that we didn't get a C is using this one to solve for time. And we'll work on that one at a later date. If we use that one to solve for time, we talked about it yesterday, we're going to have to use the quadratic formula to solve for the t, which is just math. You guys can handle that. Okay? So keys to multi-step problems. Final velocity of this section equals the initial velocity of the next section. That's one thing that sometimes kids struggle with. Okay? So there's a multi-step kinematic problem example.